What if the key to understanding our solar system's past, and perhaps life beyond Earth, lies in the swirling storms of a planet so vast it could swallow Earth whole? Welcome to the epic tale of Jupiter, the cosmic giant. Embark on a thrilling voyage to the heart of our solar system, where Jupiter, the colossal gas giant, reigns supreme, captivating us with its grandeur and mystery. Known as the king of planets, Jupiter's immense size, turbulent storms, and enigmatic moons make it a celestial marvel. In this video, we'll dive into its dynamic atmosphere, powerful magnetic field, and the moons that orbit like a miniature solar system. We'll trace humanity's quest to unravel its secrets through historic and ongoing missions, revealing Jupiter's role in shaping our cosmic story. Prepare to be awed by the majesty of Jupiter, a world of endless storms, magnetic might, and wonders that stretch the limits of imagination. Jupiter, the titan of our solar system, is a gas giant of unparalleled scale and influence, orbiting 778 million kilometers from the Sun in a slightly elliptical path that takes 11.86 years to complete. With a diameter of 139,120 kilometers, over 11 times Earth's, it boasts a volume that could engulf 1,300 Earths. Its mass, 318 times that of Earth, makes it 2.5 times more massive than all other planets combined. Yet its density is low, only a quarter of Earth's, due to its gaseous nature. Named after the Roman god of the sky and thunder, Jupiter has been a beacon in the night sky for millennia, revered by ancient Babylonians, Greeks, and Chinese as a symbol of divine power. Its rapid 10-hour rotation, the fastest of any planet, flattens it into an oblate spheroid, bulging at the equator and creating a dynamic, ever-changing appearance. Jupiter's composition, primarily 90% hydrogen and 10% helium, mirrors the Sun's, suggesting it could have ignited into a star if it had accumulated more mass during the solar system's formation 4.5 billion years ago. Its structure is layered, a turbulent cloud deck of ammonia and water vapor, a mantle of liquid and metallic hydrogen under immense pressure, and a rocky core estimated at 10-20 Earth masses. This near-stellar makeup makes Jupiter a critical piece in the puzzle of planetary formation, preserving the primordial materials of the solar nebula. Its faint ring system, discovered by Voyager 1 in 1979 and composed of dust from its moons, adds to its mystique, though it pales compared to Saturn's. Jupiter's colossal gravity shapes the solar system's architecture. It stabilizes the asteroid belt, trapping millions of objects between Mars and itself, and influences the orbits of inner planets, including Mars, through subtle gravitational nudges. By capturing comets and asteroids, like the dramatic impact of Comet Shoemaker-Levy 9 in 1994, which left scars larger than Earth, Jupiter acts as a cosmic shield, reducing threats to inner planets. Its gravity likely triggered the late heavy bombardment 4 billion years ago, a barrage of impacts that sculpted the surfaces of Earth, the Moon, and other bodies, possibly delivering water to our planet. This protective role underscores Jupiter's nickname, the solar system's vacuum cleaner. Since Galileo Galilei's observations in 1610, Jupiter has captivated astronomers, its bright presence visible to the naked eye, and its cloud bands discernible through early telescopes. Its cultural significance spans civilizations, from the Babylonian Marduk to the Chinese Wood Star, reflecting humanity's fascination with its brilliance. Today, Jupiter's study reveals clues about gas giant formation, the solar system's early dynamics, and even exoplanets, as many discovered worlds resemble Jupiter in size and composition. Its gravitational dominance and preserved chemistry make it a time capsule, offering a window into the chaotic birth of our cosmic neighborhood. Jupiter's atmosphere is a turbulent masterpiece, a swirling canvas of storms, vibrant bands, and chaotic weather patterns driven by its blistering 10-hour rotation, the fastest of any planet. Lacking a solid surface, its outer layer is a dynamic cloud deck, with temperatures averaging 108 degrees Celsius at the top, though plunging to thousands of degrees deeper within. The atmosphere is a complex brew of gases, primarily hydrogen and helium, with traces of ammonia, methane, and water, vapor, that form towering clouds. These clouds create Jupiter's iconic appearance, light-colored zones of rising gas and dark belts of sinking gas, sculpted by jet streams that roar at speeds up to 600 kilometers per hour. The interplay of these bands, stable for centuries, yet ever-shifting, paints a picture of relentless energy. The Great Red Spot, a colossal anticyclonic storm, is Jupiter's most iconic feature, spanning 16,000 kilometers, twice Earth's width, and churning with winds up to 680 kilometers per hour. Observed since at least 1665, possibly earlier, this crimson vortex has raged for over 350 years, though recent data from NASA's Juno mission shows it shrinking, now 1.3 times Earth's size. Its vivid hue, likely from chemical reactions involving ammonium hydrosulfide and organic compounds, stands out against the pale cloudscape. Juno's observations reveal the storm extends over 300 kilometers deep, rooted in the atmosphere's turbulent layers, a testament to Jupiter's enduring dynamism. Jupiter's atmosphere is powered not just by solar heat, but by significant internal energy, roughly equal to the sunlight it receives, generated from its formation and radioactive decay in the core. This internal heat drives convection, fueling storms and maintaining the banded structure. At the poles, Juno discovered stunning hexagonal cyclone patterns, clusters of massive vortices, some larger than Earth, locked in a geometric dance. These polar cyclones, unlike anything seen on other planets, highlight the atmosphere's complexity, with winds and temperatures varying dramatically by latitude. Beneath the visible clouds, the atmosphere transitions dramatically. Pressure and temperature soar with depth, compressing hydrogen into a liquid state around 1,000 kilometers down, then into metallic hydrogen, a conductive, liquid metal layer, at depths of 10,000 kilometers. This metallic hydrogen, encircling a rocky core possibly 10-20 times Earth's mass, is the engine of Jupiter's magnetic field and atmospheric vigor. The extreme conditions, with pressures millions of times Earth's and temperatures reaching 20,000 degrees Celsius, make Jupiter a natural laboratory for studying matter under intense forces. Studying Jupiter's atmosphere unlocks secrets of gas giant formation and evolution. Its weather patterns mirror those of hot Jupiters, exoplanets orbiting close to their stars, where extreme temperatures drive similar storms. By modeling Jupiter's jet streams and storms, scientists refine predictions for these distant worlds, many detected by telescopes like Kepler and TESS. Closer to home, the atmosphere's dynamics echo Earth's jet streams, which shape weather and climate, offering insights into our planet's atmospheric cycles. Juno's microwave radiometer data, piercing the cloud layers, has revealed unexpected asymmetries in ammonia distribution, suggesting deep atmospheric mixing that challenges existing models. Jupiter's atmosphere, with its timeless storms and vibrant bands, is a window into the physics of planetary climates both in our solar system and beyond. Jupiter's magnetic field is a cosmic juggernaut, the strongest of any planet, with a strength 20,000 times greater than Earth's, capable of generating forces that dominate its surroundings. This immense field is produced by the dynamo effect within Jupiter's metallic hydrogen layer, a conductive liquid metal region deep within the planet where its rapid 10-hour rotation stirs powerful electric currents. The field's intensity creates a magnetosphere stretching up to 7 million kilometers, sometimes extending beyond Saturn's orbit, making it the largest structure in the solar system visible to telescopes. This magnetosphere is a complex shield with a bow shock where it meets the solar wind, a magnetopause defining its outer boundary, and a magnetotail stretching far into space, sculpted by the interplay of Jupiter's field and solar particles. The magnetosphere traps high-energy particles, electrons, protons, and ions, forming radiation belts 10,000 times more intense than Earth's Van Allen belts. These belts, concentrated near Jupiter's equator, pose severe challenges for spacecraft, requiring heavy shielding for missions like Juno to survive doses equivalent to millions of dental X-rays. The radiation fuels spectacular auroras at Jupiter's poles where charged particles spiral along magnetic field lines and collide with atmospheric gases like nitrogen and hydrogen, producing glowing displays in ultraviolet, infrared, and visible light. Juno's observations since 2016 have revealed these auroras' 3D structure, showing they penetrate deep into the atmosphere and are driven by complex particle accelerations, unlike Earth's simpler auroral ovals. Jupiter's magnetic field interacts dynamically with its moons, particularly Io, the innermost Galilean moon. Io's 400-plus volcanoes, driven by tidal heating, spew sulfur and oxygen ions into space, creating a dense plasma torus, a glowing ring of charged particles encircling Jupiter at Io's orbit. This torus, with temperatures reaching 100,000 degrees Celsius, is a hotbed of electromagnetic activity, driving million-ampere electric currents between Jupiter and Io. These currents trigger intense radio bursts, first detected from Earth in 1955, which vary with Io's position and Jupiter's rotation, making Jupiter a natural radio beacon studied for decades. The torus also feeds the radiation belts, amplifying their intensity and influencing the magnetosphere's dynamics. The magnetic field's influence extends to Jupiter's atmosphere, where it shapes weather patterns by channeling charged particles that drive storms and heat the upper layers. Juno's magnetometer has uncovered surprising asymmetries in the field, with stronger patches in the northern hemisphere and weaker ones in the south, suggesting a more complex core structure than a simple rocky mass. These findings, combined with gravity measurements, indicate the metallic hydrogen layer may be less uniform, possibly diluted with helium or stirred by deep winds. The field's irregularities also link to atmospheric dynamics, as magnetic forces couple with jet streams, influencing the banded cloud structure. Studying Jupiter's magnetic field offers profound insights beyond our solar system. Its scale and complexity mirror those of magnetized exoplanets and brown dwarfs, where strong fields shape atmospheres and habitability. For instance, hot Jupiters orbiting close to their stars likely host similar magnetospheres, and understanding Jupiter's field helps predict their behavior, aiding missions like JWST. The Io plasma torus provides a model for accretion disks around young stars, where magnetic fields channel material. Closer to home, Jupiter's magnetosphere is a magnified analog of Earth's, which shields us from solar wind and drives space weather, affecting satellites and power grids. By studying Jupiter's auroras and radiation, scientists refine space weather forecasts, critical as humanity ventures deeper into space. Jupiter's magnetic field, a symphony of power and precision, is a cosmic laboratory illuminating the forces that govern planets, stars, and our own world. Jupiter's moons, numbering over 90, form a miniature solar system, with the 4 Galilean moons, Io, Europa, Ganymede, and Callisto, captivating scientists and stargazers alike. Discovered by Galileo Galilei in 1610, these moons revolutionized astronomy by proving that not all bodies orbit Earth, laying the groundwork for the heliocentric model. Each moon is a distinct world, shaped by Jupiter's immense gravity, tidal forces, and orbital dynamics. With the inner three locked in a 1-2-4 resonance, Io orbits twice for every one of Europa's orbits, which in turn orbits twice for every one of Ganymede's. This resonance amplifies tidal heating, driving geological activity that makes these moons some of the most dynamic bodies in the solar system. Io, the closest at 421,800 kilometers from Jupiter, is a volcanic inferno, the most geologically active body known. Over 400 active volcanoes, like Loki Patera, which spans 200 kilometers and erupts with molten sulfur, spew plumes up to 500 kilometers high, painting Io's surface in vivid reds, yellows, and blacks. Tidal heating, caused by gravitational tugs from Jupiter and resonance with Europa and Ganymede, generates intense internal friction, melting Io's interior and powering its eruptions. Its thin sulfur dioxide atmosphere, constantly replenished by volcanic outgassing, glows faintly under Jupiter's radiation, creating a hellish yet mesmerizing landscape unlike any other. Europa, orbiting 671,000 kilometers from Jupiter, is a frozen jewel with a smooth, icy crust crisscrossed by reddish latia, fractures and ridges formed by tidal stresses. Beneath this ice, estimated at 10 to 30 kilometers thick, lies a global ocean 150 kilometers deep, potentially holding twice Earth's water volume. This ocean, likely saline and warmed by hydrothermal vents on the seafloor, mirrors conditions where life thrives on Earth, making Europa a prime target for astrobiology. Its chaotic terrain with jumbled ice blocks suggests recent geological activity, possibly driven by ocean currents or upwelling. The prospect of microbial life in Europa's depths, sustained by chemical energy from vents, fuels excitement for missions like NASA's Europa Clipper, set to launch in 2024, which will probe the ocean's habitability. Ganymede, at 70,400 kilometers and 5,268 kilometers in diameter, is the largest moon in the solar system, surpassing Mercury. Its surface is a mosaic of ancient, dark, cratered regions and younger, grooved terrain where tectonic forces have stretched and fractured the icy crust. Ganymede is unique among moons for generating its own magnetic field, likely from a molten iron core or a subsurface ocean of salty water, which interacts with Jupiter's magnetosphere, creating auroras and shielding it from some radiation. This ocean, estimated at 100 kilometers deep, lies beneath 150 kilometers of ice, making it less accessible than Europa's but equally intriguing. Ganymede's geological diversity and magnetic activity suggest a complex history, with tidal heating from resonance playing a lesser but still significant role. Callisto, the outermost at 1,882,700 kilometers, is a heavily cratered relic, its surface among the oldest in the solar system, dating back 4 billion years. The Valhalla Basin, a 3,800-kilometer-wide impact scar with concentric rings, is its most striking feature, evidence of a violent past. Unlike its siblings, Callisto experiences minimal tidal heating due to its distance, yet evidence from Galileo's magnetometer suggests a subsurface ocean, possibly 200 kilometers deep, sustained by residual heat or chemical interactions. Its battered, icy surface, coated with dark dust, contrasts with the active geology of Io and Europa, offering a glimpse into the solar system's early bombardment phase. Callisto's relative stability makes it a potential base for future human exploration of the Jovian system. These moons likely formed from the same solar nebula as Jupiter, coalescing in an accretion disk around the young planet, much like planets, formed around the Sun. Their compositions, rocky cores with icy or volcanic surfaces, reflect the temperature gradient in this disk, with Io's heat-driven volcanism contrasting Callisto's frozen stasis. Their orbital resonance stabilizes their paths, but fuels geological activity, a dynamic balance unique to the Jovian system. The Galilean moon's diversity mirrors the variety of exomoons, likely orbiting gas giants in other star systems, detected indirectly by telescopes like JWST. Studying them refines models of satellite formation, tidal evolution, and planetary migration applicable to systems like TRAPPIST-1. The moon's astrobiological potential, particularly Europa's, captivates scientists. Europa's ocean, with possible chemical nutrients from the seafloor, parallels Earth's deep-sea vents where life thrives without sunlight. Ganymede and Callisto's oceans, though deeper and less active, expand the search for habitable environments. The moon's interactions with Jupiter's radiation belts, producing oxygen in Europa's ice and fueling Io's volcanoes, create chemical cycles that could support life. Future missions, like ESA's JUICE, targeting Ganymede, will complement Europa Clipper's work, mapping these worlds' surfaces and interiors. The Galilean moons, each a testament to nature's creativity, offer profound insights into the conditions that shape worlds and the tantalizing possibility of life beyond Earth. Humanity's exploration of Jupiter has been a monumental endeavor, a testament to ingenuity and curiosity that has unveiled the planet's complexity over decades of ambitious missions. The journey began with NASA's Pioneer 10 in 1973 and Pioneer 11 in 1974, the first spacecraft to brave Jupiter's intense radiation belts. Equipped with instruments like ultraviolet photometers, magnetometers, and plasma analyzers, these probes mapped the planet's magnetic field, measured its helium abundance, confirming its sun-like composition, and captured early images of its cloud bands. Despite radiation damage that scrambled some data, the pioneers survived their flybys, revealing Jupiter's harsh environment and paving the way for future exploration. Their success marked humanity's first venture into the outer solar system, igniting scientific and public excitement. The Voyager 1 and 2 missions, launched in 1977 and reaching Jupiter in 1979, transformed our understanding with unprecedented detail. Voyager 1's images revealed Io's volcanic plumes, some soaring 300 kilometers high, proving it the most volcanically active body known. Voyager 2 captured Europa's cracked, linear-covered surface, hinting at a subsurface ocean, and detected Jupiter's faint ring system, a delicate band of dust from its moons. The spacecraft's high-resolution cameras showcased the great red spot's swirling chaos and Ganymede's grooved terrain, while plasma detectors measured the Io plasma, Taurus's charged particles. Voyager's images, broadcast globally, captivated millions, with media outlets dubbing Jupiter a cosmic art gallery. The mission's golden record, carrying Earth's sounds and images, symbolized humanity's outreach to the cosmos. With Jupiter as its first stop, the Galileo mission, launched in 1989 and orbiting Jupiter from 1995 to 2003, provided an in-depth study of the Jovian system. Galileo's atmospheric probe, plunging 150 kilometers into Jupiter's clouds, measured wind speeds up to 640 kilometers per hour, confirmed lightning, and analyzed the atmosphere's composition, revealing unexpected helium and water scarcity. The orbiter's magnetometer confirmed Ganymede's magnetic field and detected induced magnetic signals on Europa and Callisto, suggesting subsurface oceans. Galileo's images of Io's Loki Patera eruptions and Europa's chaos terrain fueled astrobiology debates, while its study of Callisto's Valhalla Basin offered clues to the solar system's bombardment history. Despite a crippled high-gain antenna that reduced data transmission to a trickle, Galileo's 8-year mission, powered by radiation-hardened electronics, delivered 14,000 images and reshaped planetary science. NASA's Juno mission launched in 2011 and orbiting Jupiter since 2016, has peered deeper into the planet's mysteries with cutting-edge technology. Juno's microwave radiometer probes atmospheric layers up to 600 kilometers deep, revealing ammonia asymmetries and deep jets driving the Great Red Spot, which extends over 300 kilometers. The Jovian Auroral Distributions Experiment, JADE, maps auroral particle flows, while the magnetometer uncovers field asymmetries, suggesting a complex metallic hydrogen layer. Juno's high-resolution JunoCam, engaging public participation through image selection, has captured polar cyclones in stunning detail, with hexagonal patterns mesmerizing viewers worldwide. Juno's extended mission, ongoing into 2025, includes flybys of Io, Europa and Ganymede, refining orbital data and imaging their surfaces. The spacecraft's radiation-hardened vault, shielding its electronics, exemplifies technological leaps since Pioneer's era, enabling prolonged study in Jupiter's harsh environment. Future missions promise to deepen our understanding, with international collaboration driving innovation. NASA's Europa Clipper, launching in October 2024, will conduct 50 flybys of Europa, using ice-penetrating radar to map its ice shell and mass spectrometers to analyze ocean-derived particles in plumes. The mission aims to confirm the ocean's depth, salinity and habitability, potentially detecting organic compounds. ESA's Jupiter Icy Moons Explorer, JUICE, launching in 2023 and arriving in 2029, will focus on Ganymede, orbiting it to study its magnetic field and subsurface ocean, while also observing Callisto's geology and Europa's surface. JUICE's laser altimeter and sub-millimeter wave instrument, with contributions from JAXA, will map moon topographies and atmospheres with unprecedented precision. These missions, backed by thousands of scientists across NASA, ESA, and global institutions, leverage decades of data from Voyager and Galileo, showcasing humanity's growing expertise in deep space exploration. Jupiter's exploration has transcended science, leaving a cultural legacy. Voyager's golden record, carrying Bach and Chuck Berry, immortalized Jupiter as a waypoint in humanity's cosmic message. Galileo's discoveries inspired films and novels, while Juno's vivid images, shared on social media, have made Jupiter a public phenomenon, with citizen scientists naming cyclones. The mission's technological advancements, from radiation-resistant electronics to precise navigation, have spurred innovations in telecommunications and robotics, benefiting Earth. The collective effort of engineers, scientists, and communicators, over 10,000 for Juno alone, has turned Jupiter into a beacon of human ambition, its storms, rings and moons inspiring generations to dream of distant worlds and the possibilities they hold. Jupiter, the cosmic titan, is a realm of relentless storms, magnetic power, and moons that spark dreams of discovery. Its great red spot roars, its magnetosphere hums, and its moons, like Europa, hint at hidden oceans. Jupiter humbles us with its vastness, reminding us of Earth's fragile place, yet inspires us to reach for the stars. As we await new missions, it beckons. Could Europa's depths hold life, redefining our cosmic story? Jupiter teaches us resilience, showing that even amidst chaos we can endure and shine, like its storms persisting for centuries. It urges us to find purpose in challenges and embrace our potential. How can we, like Jupiter, stand bold and inspire others? Let its story stir you to dream grander and cherish life's fleeting beauty. Share your thoughts in the comments. We want to hear your ideas. Like, share, subscribe, and follow our social media, linked below. Knowledge is an investment with inexhaustible returns.